Alright, in the previous video, I was calculating the pI of an amino acid that does not have an ionizable R group. Next, I want to do something a little bit harder, which is figure out the pI, eventually, for an amino acid that does have an ionizable R group. And I'm going to pick a kind of tricky amino acid, histidine, because when I look at the chart, the side group of histidine is not yet protonated. I need to know where it's protonated, what the starting charge is at pH 1, and then do the process that we did in the previous video to figure out the pI. Histidine is a basic amino acid, meaning that when you throw it into water, it at pH 7 or less, chances are it will be protonated. The problem with histidine, though, is that pH 7 is not yet quite acidic enough to protonate the side group or the R group. Let us try to analyze where the molecule will be protonated at pH 1, because that is the trick I am using when I figure out the pI. If you recall from the previous video, the starting point is pH 1 over here. And then I slowly add base to increase the pH to start ripping off the protons one by one off of the ionizable groups. So that is my first task. What does it look like at pH 1? And what is the total charge at pH 1? To answer that, I need to know which nitrogen is most basic. And so am I going to have something like this? Or am I going to have something like that? Which nitrogen will rip off that proton? If you remember aromaticity, you will know that this lone pair is part of the pi system to make it aromatic. This lone pair is not part of the pi system because it already has a pi bond, meaning that this lone pair is in an sp2 orbital, because the p orbitals are being occupied already to make the pi bond. And I'm not going to go over this, but that's sp2 orbital, and this is in a p orbital. Okay, which one is more available? The one in sp2, because the lone pair in the p orbital is part of resonance, as part of the aromaticity of the molecule, and it's circulating. It's not available to grab that H. My guess is this. Okay, it's the orange arrow that works. My guess is this one here. Okay, it is the place of protonation. Okay, now there's another way to go about this. We can look at stability of the conjugate acids, right? These are the conjugate acids. Conjugate acid. Conjugate acid. Okay? Our two options are shown. This option here is more stable because resonance. Look at this. If I do this, I get a resonance structure. See, I was setting up, like, is this resonance structure coming from here or coming from here? It's coming from here. And look what I have now. I'm going to fill in the rest. I have an H here. There's a double bond there. There's positive. There's an H here. And a lone pair. Not positive. That's resonance stabilize. So this is resonance stabilize, meaning that the nitrogen here is more basic. This is what I should be drawing. I should not be drawing this. This one has no resonance. It's less likely to happen. No resonance. Now, you shouldn't take my word for it, right? You should try. Double check. Or guess. I mean, could you do something like this? No, because that nitrogen would not satisfy the octet rule. So don't do that. There's no way I can move the electrons to start delocalizing this charge. Do you see how the charge was delocalized here? It went from here to this nitrogen. So that's great. Resonance delocalized the charge. It's more likely to protonate at this position here. Okay. I don't want to belabor the point, but at pH 1, you could either draw this. You should draw this. Okay? Or you could draw this. I can't take off points for that, but this is your initial drawing up here. Remember, at pH 1, what did the amine and carboxyl group do? See, at pH 1, it's protonated for the amine, and it's neutral, protonated and neutral for the carboxyl group. Think of the terminology. Protonated and positive, protonated and neutral. Okay, great. So for histidine, I said I'm going to do the shortcut. I'm not going to do the full shortcut. I want to at least draw the beginning at pH 1. So at pH 1, we have the protonated amino group. We have the protonated carboxyl group, which is neutral. And now you're testing me. Do I remember the structures for histidine? 5-membered ring. Oh boy. N. This one had the H. Fully protonated, meaning this will get, I think this was protonated and this is positive. What am I reminding myself of? I'm reminding myself of this molecule here. That is identical to this. So the pH is 1, okay? The pH is 1. I get it fully protonated. But look at the charge. It's different than what we had before. The fully protonated for glutamine is +1. Here, +1. For histidine, it's +2. You see the two charges? So this is charge +2. Okay. Now let me show you the shortcut. Again, our goal is to figure out the PI. Okay. So here's the shortcut. Let's list the pKa's for histidine. Histidine is over here, 1.8. Let's use the color. Let's use red. 1.8, 9.2, and 6. 1.8 is for the carboxyl, 9.2 is for the amino, 6 is for the side group. 1.8, 9.2, 6. 1.8. pKa 9.2. And this one here, pKa 6. 1.8, 9.2, 6. And make sure they match the correct group. 1.8 for the carboxyl. 1.8 for the carboxyl, 9.2, and 6. Perfect. Okay. What do the pKa's mean? When you cross over the pKa, you get rid of the H. Okay, not all the H's. In this case, one of the H's. Okay, so here's the shortcut without drawing. The first pKa I'm going to cross over is 1.8. So let's pick a number above 1.8. Let's say pH equal to 2 or 3 or 4. I just can't go above 6 because these two are neighbors to each other. So let's pick 4. Well, the charge, what happens to the charge? When we cross over 1.8, we get rid of this hydrogen. So think about it. Positive, negative, positive, plus 1. And it will always do that. It will go down by 1 exactly. Plus 1. Okay? See, without drawing it, I know the charge is plus 1. I could analyze this and get rid of this H. Or I could know that it goes down by 1 each time. pKa, what's the next pKa? The next pKa to cross over is 6. So let's pick pKa of, I can't go above 9. I have to be above 6 though. pKa of 8. Let's try that. Sorry, pH of 8. Okay, what do you think happens to the charge? Without looking, charge is now 0. Now with looking, what happens here? This was already negative, and then when we cross over 6, this becomes neutral. So look at that, negative and positive, that's neutral. And I ran out of space, but let's go down here. Let's cross over the 9.2 pKa. So maybe we could say a pH of 11. That is basic enough now to remove one of these hydrogens here. Okay, what happened to this charge? Well, let's remind ourselves. This was negative, this was neutral, and now when we cross over 9.2, we get rid of this charge here. We're net negative. So now the charge is minus 1. The rule for PI is you average the pKa's that sandwich the neutral species. Here's the neutral species. Those are the two pKa's sandwiching the neutral species. PI equals 6.0 plus 9.2 divided by 2. 6.0 plus 9.2 divided by 2. This is 10.6. That is the answer for the PI for histidine. The shortcut is I'm not drawing all the structures. I am a little bit unsteady picturing it in my head, so I draw the first structure so I could refer to it as I strip off hydrogens as I cross over the pKa's. You will still need to know how to draw the structure. So between pH 1, 4, 8, and 11, let's pick 4. Let's pick the next one. So what does it look like at pH 4? Let's not circle it. Well, at pH 4, we cross over the 1.8, but we didn't cross over the 6 or the 9.2, so we're going to get rid of this. Do you see actually how important the first structure is? Because I'm basing all of my answers off of the first structure. So I crossed over pK 1.8, so now I take off that hydrogen to become negative. Everything else stays the same. This is very easy for me once I have the structure at pH 1. If I screw up this structure, by the way, then everything else gets screwed up. The charge gets screwed up, the structure will get screwed up, and possibly even the PI will get screwed up. So this is the important structure. What does it look like at pH 1? Right now, for pH 4, we have that. Is it truly plus 1? Plus negative is plus 1? Yeah, I predicted it was plus 1. At home, Okay, do the one for 8. pH equals now 8. What does that look like? We already have 4. We could work off of this if you want. At pH 8, we crossed over the 6. So we are able now, we're basic enough to get rid of this H here and this plus charge here. At 8, I predicted it was neutral charge. And so when we get rid of this, look at that, negative and positive, the Zwitter ion. So you would draw the Zwitter ion, this one right here, without the H and positive charge here. Okay. Fully deprotonated, right? pH 11. pH equals 11. That is basic enough to do what? Basic enough to get rid of that, basic enough to get rid of that, basic enough to get rid of that. 1 hydrogen each. Okay? You'll do 8 on your own. When I think of very basic, or pH 11, 12, 13, and I'm above the pKa for all the groups, then I know that the amine is neutral. I know that the carboxyl group is deprotonated. And I know also that the side group now has been deprotonated. So take a look at what I'm about to draw. Do I get rid of this H, by the way, this here? No, this is not acidic, okay? We get rid of this H and we're done. Don't over deprotonate, right? This has no pKa. I mean, it has no pKa between 1 and 14. The pKa of this is, I don't know, maybe 36, maybe a little bit lower. But again, we're just going from 1 to as high as 13. Okay, here we did 11. That H is still there. Okay, that H is still there. The H that we removed was this one. Okay, and we get back to neutral. Let me draw this a little bit better. Yikes. Did I draw this right, actually? Yeah, it's aromatic. And let me just make this one a little bit straighter. Okay. Net -1 right there. Okay. All right. That is the last page of this handout. This shows you how to calculate the PI for, in this case, histidine. You could always practice, because I don't have the PI here, but you could look up the PI. Look up the PI for instance, cysteine. Look at cysteine, actually. We're going to look at the structure in just a bit. Cysteine is right here. Let's use purple. Cysteine, it has 1, 2, and has an ionizable side group. Okay? Do your calculations, draw your structures, get a PI. Then look it up. Look up the cysteine PI and see if you match. What I want to show for the structure for the cysteine is this 8.3. Cysteine is right there. pKa 8.3. This dude right here. So what is at the border of? It's the border between neutral, and if you're above 8.3, this become negative. Okay. What you want to know for sure is that for each of these ionizable side groups, do you know what the transition is? Are you going from, for instance, positive to neutral when you lose a proton? Or are you really going from neutral to negative when you lose a proton? They're both losing protons. Once you cross over these, you become basic enough to lose a proton. It just really, really, really matters. How did you start? How did you start? With histidine, we started with it being positive. Okay? All right. If you really need explicit directions, figure out the PI for aspartic acid. Okay, we did this one, the basic amino acid. Can you do the PI for an acidic amino acid? Okay. The aspartic acid is right here. And we have a 3.9er. Okay. What does that mean in relationship to this? Whoa. pKa equals 3.9. Well, we have no proton here at pH 7. At pH 7. So at pH 7, it was basic enough to get rid of the hydrogen that was here. What this 3.9 means is that below 3.9, there's an H. Above 3.9, like pH 7, there's no H. Okay. All right, I'll stop talking now. Maybe there'll be a third video where we practice what does pH 1 look like for each of these ionizable groups. What does pH 1 look like? If you could do that, get the pH 1 perfectly correct, pH 1 here, and pH 1 here. If you could get that perfectly correct, the rest of the problem becomes easy and accurate. Your answer will be accurate.